So let us make a circuit using the FET and let's see how it operates. All right, we'll draw the circuit exactly in the same way that we drew for BJT. We have some input voltage and some, well, we actually don't need any resistance in this case. Well, let me put the resistance just for consistency. Okay, then comes our FET. This is our FET. Finally, here we have another resistance, and as before, exactly like the BJT, we will need a supply voltage. Okay, all right. Okay, so let's try to do some of the analysis that we did using BJT for the FET. Okay, we will put in some values. Suppose I exactly like the BJT, I put here 1K and I put here 2K and my supply will be 20 volt. And well, I will change the input, so I will put different values at the input, and for this FET I will choose GM equals to 2. Okay, so let's see what values do we get. So so if I put a voltage of 1 volt at the input, okay, first of all, will any current flow in the input loop? Will any current flow here? Well, no current will flow here, because as you can see that this is an open circuit, right? This is an open circuit. There is no connection in this place, so no current can flow. But we don't need any current to flow in a FET, right? Because, well, a FET is not current controlled, it is voltage controlled, okay? So even if there is no current in this direction, there will still be a voltage here, all right? There will be a voltage at these two terminals. So what will be the value of this voltage? VGS. If no current flows in this direction, then there will be no drop in this resistance, and the input current will be directly pass to the G and S terminal. Okay, this is our G, this is our S, and this is our drain. All right. Okay, so the input voltage will be directly transmitted to the GS terminal. So the VGS will be, well, exactly equal to the input voltage. The input voltage is 1 volt. All right. If VGS is 1 volt, then what is the value of ID? If we call this current ID, what is the value of ID? Well, since ID is related to VGS by the relation ID equals GM VGS, since VGS is 1 volt, GM is 2, then ID will be 2 milliampere. Okay, oh, I should be careful about the units. As we saw in the case of BJT, that beta didn't have any unit. Why? Because, well, beta was of the form IC equals beta IB, right? Here, IB has a unit of current, IC has a unit of current, so beta has no unit. But for this relation, you can see that this side has a unit of voltage and this side has a unit of current. Okay, so the unit of GM will be current by voltage. So we usually measure currents in milliamperes and measure voltages in volts. So the unit of GM will be milliampere per volt. Okay, the unit of GM will be milliamperes per volt. All right. So if VGS is 1 volt, then if we multiply by 2 milliampere per volt, then ID will be 2 milliampere. All right. If ID is 2 milliampere, then what will be the value of this resistance, the V2K? I mean the voltage across this resistance, V2K. Okay. Since ID is flowing through this 2K resistance, then the voltage, exactly like our BJT case, the voltage will be 2 volt, right? If 2 milliamp, oh sorry, this will be 4 volt. If 2 milliampere current is flowing through 2 kilo ohm, then this voltage will be 4 volt. And finally, if this is 2 volt, and if then what will be the voltage across D and S? Okay, what will be the voltage across the transistor? What will be the voltage VDS? Okay, the voltage between these two terminals, between D and S. Well, if the supply is 20 volt and the resistance is consuming 4 volt, right? If the resistance is consuming 4 volt, then VDS will be, well, 20 minus 4 volt, right? It will be 16 volt. Simple as that. Okay, exactly like BJT, except for BJT our control parameter was the current IB, and for FETs our control parameter is the voltage VGS. Except that everything is similar. Okay, so we will continue exactly like our BJT case. Suppose I input a voltage of 2 volt. I input a voltage of 2 volt. Then for 2 volt, what will be these values? VGS will be equal to the input, so this will be 2 volt. ID will be 2 times 2 volt, it will be 4 milliampere. V2K will be 4 times 2, again 8 volt, and VDS will be 20 minus 8, 12 volt. Okay, so I will just cut to the chase, and if I input 5 volt here, then VGS will be 5 volt, ID will be 10 milliampere, V2K will be 20 volt, and VDS will be 0 volt. Okay, 20 minus 20 equals 0. So same as the BJT, you can see that at 10 milliampere current, the VDS, the voltage of the transistor, has become 0 volt. Now if I increase the voltage, input voltage, even further, increase it to 6 volt, then what will happen? Well, VGS will be 6 volt. Well, I should write this using red. VGS will be 6 volt. Now, if the current ID follows this relation, okay, still follow this, sorry, still follows this relation, then what will happen? Well, Gm equals 2, right? Then if the current, if the VGS is multiplied by 2, then the current will become, well, 12 milliampere. But for that, V2K will become 24 volt. As we saw in the BJT case, well, this is not permissible. Why? Because the supply is 20 volt, right? Since the supply is 20 volt, this resistance cannot consume 24 volt, because in that case the transistor would have to produce a voltage on its own, and the transistor cannot do that. So what will happen if I apply 6 volt to it? Okay, so since the maximum voltage of the resistance can be 20 volt, right? The maximum voltage can be 20 volt. So the maximum value of ID can be 10 milliampere. The value of ID cannot exceed 10 milliampere for this circuit. So even if I apply 6 volt, then since ID has reached the maximum value, it will not increase any further. So if I apply 6 volt, the current will still be 10 milliampere. Alright, and the voltage across the resistance will still be 20 volt, and the voltage of VDS will be constant at 0 volt. Okay, so even if I apply 7 volt here, nothing will change, only VGS will change. Okay, VGS will become 7 volt, but the ID will still be 10 milliampere, and V2K will still be 20 volt, and VDS will still be 0 volt, and it will go on like this. So exactly like the BJT case, the same things are happening. So if I draw the transfer characteristics, all right, if I draw the transfer characteristics here, okay, the y-axis is my ID and the x-axis is my V-in or VGS, whatever you please. Okay, so initially when VGS was increasing, as we can see, when VGS was increasing, the current was increasing. Okay, the output current was increasing. So initially when VGS is increasing, ID will increase. But after ID reaches a maximum value, ID becomes constant. Okay, ID does not change any further. ID becomes constant. Even if VGS increases, see, VGS is still increasing in this direction, but ID does not increase. Okay, so it will be like this. All right. So for the so when this happens, okay, when ID becomes constant, then you can see that VDS becomes 0 volt, right? VDS becomes constant and 0 volt. So exactly like the BJT, if VDS is constantly at 0 volt, then this will be equivalent to a short circuit. Okay, this will be equivalent to a short circuit. All right, so we can in this graph, okay, in this graph, this was the amplification region, and this part was the short circuit region. Okay, there is a naming difference here. In the case of BJT, we call this the active region, and we call this region the saturation region. But in the case of a FET, the naming is a bit different. Okay, we will discuss the naming a little later, but for now we can just call them the amplification region and the short circuit region. Still, just in the case of BJT, the graph is still not complete. What happens if we apply a negative voltage at the input? Okay, that might be the question. So when we will see how a FET is fabricated, how a FET is made, actually constructed, you will see that if you apply a negative voltage at the input, then no current actually flows through the output. Okay, the output becomes open circuited. So if no current flows to the output, then ID is 0. So if ID is 0, then for negative VGS, the graph will look like this. All right, simple as that. So we can call this the open circuit region. Okay, this is the open circuit region. So exactly like BJT also had an open circuit region and an amplification region and a short circuit region. A MOSFET or FET, okay, a FET also has an open circuit region, an amplification region, and a short circuit region. All right. So in the next lecture, we will try to find out the voltage transfer characteristics of this amplifier configuration that we made using a FET. Thank you.